class. Yeah. The first example, the reason we spend so much time, one is we talk about problem solving basics. So we've spent a lot of time on that. Also, another part we spend a lot of time. We establish that decay model. So we derive that decay model, so we spend a lot of time. Yeah. After that, now we can use decay model directly, so we hope we can save a lot of time. Yeah. All right, so for the second example, 8.2, the title, Subsonic Flight. Yeah. Let's look at the question number 2 first. Yeah. Yeah, so about the flight like that. Yeah. So the question, the efficiency of the engines of subsonic airplanes depends on air pressure. Yeah. Air pressure. And is usually the maximum at 36,000 feet. Yeah. Yeah. So here we consider this flight, the maximum height it can fly, that high. All right. Yeah. At 18,000 feet, it is half its value. This is the value of the pressure. Okay. Yeah. Air pressure. Yeah. Remember here we are talking about the air pressure. So the y function is the air pressure function. Okay. Yeah. All right. So air pressure, there is a function. Here we use the y. Yeah. Because the height. Yeah. Here we need to use height. Yeah. Height. Yeah. So let's use x. Yeah. Variable x, the height. Yeah. But at sea level, when the height is 0, the pressure is given. Okay. Y0. That's the air pressure. Yeah. All right. Then, this condition, at the height 18,000 feet, this height, the air pressure is half of the sea level Y0, 1/2 of Y0. Yeah. At 18,000 height, the air pressure, if we measure the air pressure, 1/2 of Y0. That condition. All right. Then the goal, we need to find the air pressure y of x at this height. This height means the maximum height. Okay. Yeah. This height means the maximum height. 36,000 feet. Yeah. Let's solve this problem. Then, remember, we have 4 steps. Yeah. All right. So, first we need to understand. Yeah. It looks like the concept. We know all the concepts, right? You know, air pressure, height, you know. Yeah. So, that part easy. So, we understand all the concepts in this question. So, let's move to the model step. Mathematical model step. Model, we need a physical law. Okay? To model, to establish the equation, we need a physical law. Okay? The physical law that tells us the rate of change of the air pressure, that's y prime of x, is proportional to the pressure. Proportional to the pressure. Constant multiple of the air pressure. That's the physical law. Okay? So based on this law, we can set up our differential equation. Yeah. Analysis. Yeah. All right. So here, if we want to go back to the problem-solving strategy, at this point, we need to use our experience. But first, because based on the physical law, we can establish the differential equation first. Yeah. So that's directly from the physical law. All right. To solve the equation, we need to use our experience. Okay? All right. Yeah. So the equation is rate of change, dy over dt, that's the rate of change, equals proportional constant multiple, constant C multiple that air pressure function y. So we have that equation. Yeah. It looks familiar, right? Yeah. That's C. Looks familiar. Yeah. That's C. Okay. All right. And it matches the form of our decay model, right? Yeah. But we know the solution. Yeah. Use our experience. We can write a solution of this equation immediately, right? Yeah. So here it saved us a lot of time. So we jump to the known solution we have. Okay? All right. So, yeah. Yeah. But here we need to change the variable to from t to x. Not time. Yeah. In the previous example, the variable is time t, but here the variable is height x. Height above the sea level x. We make a small change. Yeah. All right. So then the older solution, because we use t variable, here we need to modify it. Yeah. T variable, we should change it to x variable. All right? Yeah. By analogy. Okay? So the new solution becomes y of x equals a times e to the c x. Straightforward. Yeah. Yeah. Yeah, because the format, everything looks the same. So by analogy, so we can get a new solution immediately. Yeah. So then we need to go to the next step. Using this equation, we want to find a final answer. Yeah. All right. So let's see. Yeah. Yeah, but so that A, yeah. Remember that A corresponds to the initial value at the height 0. When x equals 0, that's the A value. Okay? Yeah. So at the height 0, the air pressure number y0, that should be the A value. So we replace A by this y0. All right? Yeah. Then, that C is an unknown constant. It's not given, but it's a constant. Unknown. You can determine it later if you like. Yeah. Here, let's just leave there. Unknown constant. Leave it there. All right? Yeah. Next. Now, what do we have so far? Solution, and then we have a condition. The air pressure value at 18,000 equals 1/2 of the y0. That's our condition. Okay? Yeah. Given, so we use that condition. Then the goal. What's the goal? The goal, we need to find y of the y air pressure value at height 36,000 feet. Yeah. That's the goal. Okay? Yeah. How to find it? The question. Yeah. There are two ways. Yeah. So there are two ways. Yeah. Yeah. All right. So here, let me explain these two ways, the solution. Constant C is unknown. The question is, do we need to find constant C first or not? Yeah. Yeah, so yeah. So you mean not necessary, right? Yeah. So here, the two ways. One way, you find constant C first. Second, you get around. You do not need to find C first. You can get around it. Okay? So here we compare these two. Yeah. Because the first way, find the C constant first, many students did that. Yeah. So when I assign homework questions, many students, so when they have the similar questions, some of the students, they like to find a constant C first. Yeah, it's okay. So your answer also correct. Yeah. But second way, we can bypass that unknown constant C. Yeah. All right. Yeah. So let's see here. Here I want to bypass that constant C. Okay. All right. So we plug in, yeah, because that's the solution. When we plug in, yeah, so we plug in x equals 18,000 after you plug in, so you get this equation. Okay? Yeah, you get that equation. All right. That equation, because it also equals, yeah. Yeah, so here we just, change the form. Yeah. From this equation to that one, we only change the form. Okay? Yeah. All right. Then the second equation, when we plug in x equals 36,000, yeah, so we have that. Okay? All right. Then we change the form, yeah, equals, yeah. So here, now we have this form. Yeah. Here, why we write this way? Yeah, because when we write in this way, we want to cancel out that C. We want to get rid of that C. Because we don't want to find that C. Yeah. Get rid of it. Yeah. So how to get rid of that C, unknown constant. Yeah. All right. So here, before we do that, yeah. So this condition tells us, yeah, y of 18,000 over y0 equals 1/2. Yeah, from the condition. Okay. Yeah. So we change a little bit. So this fraction equals 1/2. Okay. Yeah. So here you can see, yeah, because based on that condition, 1/2, you can replace this fraction by 1/2. Then e to the 18,000 times c equals 1/2. Can you solve this equation for c? Yeah, you can find the c value. Okay, if you like, you can find the c value. So that's why so many students, when they did homework, they choose this way because they feel it's simpler for their thinking. Okay, yeah, you can do that if you like. Yeah, but here I show you another way. We want to get around, bypass that c. Yeah, there is some reason. Later I will explain the reason. There is a reason why we, try very hard to bypass that c. Yeah, all right. Can you see this 36,000 is double of 18,000? Can you see that? Double. Okay. If it's double, can we say the bottom number is square of the upper number? This lower number is just a square of upper number. Yeah? If you can see, then this number is a square of that number, right? Yeah? The bottom one is square of the upper number. Yeah? Let's use that observation. Yeah? Because this number equals the square of that number. Yeah? 2 times 18,000C. Same as 16,000C. Okay? Then we look at the right-hand side. We have y of 36,000 over y0 is the square of, because the upper fraction is given 1/2. So 1/2 square, 1/4. How about that? Yeah, it's given. Yeah. So our conclusion is the air pressure y function at the height 36,000 feet, its air pressure is 1/4 of the sea level air pressure. And the maximum, yeah, so because this is the maximum of the flight, okay? The air pressure at the maximum height for the air flight equals 1/4 of the air pressure at the sea level. That's the conclusion. Okay? So the final answer.
So if they're not double, would you just have to find the factor between them?
Yes. Yeah. If it's not double fraction, so actually if it's not double, it's a good number relationship. How about you take log? Then you can do division, right? You take a logarithm. Okay? Log is natural log, right? You take a natural log, then you do division. That C is gone. Okay? Cancel out. Good question. Yeah.
Is it essential that we find the air pressure at sea level, or?
No. Yeah. Whatever it is given. So at sea level, why not? Why 0? Whatever that number is, you just copy that number. Okay? So we do not need to find it. Yeah. It's not given. Yeah. So leave there. Okay? Leave that. Why not number there? All right. Yeah. So that's our second example. But before we move to the third example, our second example, I want to explain what's the benefit for the second method we bypass that unknown constant C. Yeah, there is some benefit, some reason. Yeah, let me explain that reason first. All right. Oh, the reason. I remember. I have a place to remember. Yeah. The reason is, probably in the third example, I will explain that. But here, I just say a few words. Yeah. The reason is, when we calculate the C, you need to do calculation, right? Every step calculation, you have some computation error, right? Yeah. So when you calculate that C, you have some intermediate computation error. And at the end, you accumulate error from all the steps, right? Yeah. So if you have a lot of intermediate steps, you need to do calculation. You accumulate errors from all the steps. So at the end, your accuracy will be worse. If we can skip some intermediate steps, so we do not lose any precision in the intermediate steps. So then, at the end, our accuracy of our answer will be better. Yeah, so that's the main reason. Okay, yeah. All right, let's move to the third. Radiocarbon dating technique. Yeah. I hope I can use 30 minutes to complete this question. Yeah. All right. The good thing is because, think about, we have that decay model, the solution, we apply it, we can solve it quickly, right? So we do not need to spend a lot of time. Yeah. After we invest a lot of precious time at the beginning, we develop that model, okay, or the solution. Yeah. So then later we just enjoy the efficiency, right? So we apply it. So it can save us a lot of time. Yeah. All right. 8.3, first, the background of that radiocarbon dating technique. So it's an important technique. Yeah, first, let me explain this technique. Yeah, very important. Yeah. Method for determine the age of an object containing organic material. Okay? Yeah. Yeah. Animal, plants, yeah. So organic materials. Yeah. All right. By using the properties of radiocarbon. So what's the radiocarbon? There is one isotope, radioactive isotope of the carbon, C14. We know C is the notation for the carbon. Okay. Carbon, this element, it has 3 different isotopes. Yeah. Among those 3 different isotopes, only the C14 is radioactive. Yeah. The other 2 are not radioactive. Yeah. So this isotope, radioactive carbon isotope, it has some special usage. Yeah. It can be used to determine the, age information. Yeah. How to do it? Yeah. So, sorry. Yeah. So let me describe the method. Yeah. All right. There is a professor. Yeah. Willard Libby professor. Yeah. A physical chemist, University of Chicago. Yeah. He developed this technique. Yeah. All right. In 1949. That early. Okay. Yeah. All right. Yeah. And for this achievement, yeah, he got a Nobel Prize in chemistry, 1960. So you know how important it is. Yeah. So Nobel Prize that big. Yeah. Because use this technique. Yeah. So many, ancient, mummy, so all those things, fossil things, a lot of things. The approximate age can be determined. Approximate, yeah. So although not very accurate, but if you do not use this technique, how do you estimate the age? Right? It's hard. Yeah. But this is a scientific method to determine the approximate age. Yeah. All right. The idea is like this. Here, I use this picture. Yeah. Yeah. So now in the nature, the carbon, so animal, plants, so they contain the carbon, right? And the 3 types isotope of carbon. So in the animal body, plants, containing 3 isotopes of the carbon. Yeah. But only C14. Yeah. C12, C13, C14. Yeah. 3 different types. Only C14 is radioactive. Then, so the sun ray, cosmic radiation, apply on carbon 14, then following, so on it, beta decay, so then eventually it changes to nitrogen 14. Yeah, after, cosmic, yeah. All right. So then this isotope disappears, okay? The amount of carbon 14 is reduced during the long period of time, okay? All right, yeah, yeah. So then, then people can measure the amount of carbon 14 in the body, yeah, the percentage, yeah. Based on that percentage number, then we apply certain formula, we can estimate, approximate age number. That's the idea of this method. Okay? Yeah. All right. So here, so you know some rough idea. Okay? Next, we use this, our question number 3. Then, when we go through the solution, you can understand the details better. How to apply this method to determine the age of a mummy, yeah, a famous mummy. Yeah. All right. Oh, sorry. Yeah. All right. So this method, measuring the proportion of carbon 14 in a sample from a dead organism provides information that can be used to calculate when the organism died. Okay? Yeah. All right. So that idea. Okay? All right. Yeah. And because it follows the decay model, right? Half-life. Yeah. Radioactive. Yeah. Radioactive. And we used radium before, right? So here we just replace our radium in our first example to this radioactive carbon-14. Yeah. The same rule, same physical law we can use. Yeah. Half-life, physical law, same. Okay? Yeah. All right. Yeah. So that's the mummy. We want to determine the age. Okay? Yeah. Mummy, oats, mummy, yeah. Oatsy, mummy, yeah. All right. In September 1991, the famous Iceman, mummy, yeah. Well, yeah. And, right. But how to determine its age? Well, that's important. Okay? Yeah. How many years? Yeah. Before that time. Okay? Yeah. Yeah. All right. How to determine that? Apply that method. Okay? Carbon dating, that method. Radiocarbon dating method. So people measure the ratio. So what ratio? Carbon 14 over carbon 12. Although there is carbon 13, but carbon 13, the amount of carbon is very small, so very rare. Yeah. Yeah. So that's very small, little number can be ignored. Okay? Yeah. So you only need to measure the ratio of these two substances. Yeah. All right. Yeah. All right. Yeah. And at that time, yeah, so let's assume at 1991, people measure, find the ratio equals 52.5%. Okay? Yeah. Doing experiment in lab. Yeah. People can do several times. Yeah. Then find the average, things like that. Okay? Yeah. Yeah. So that number, percentage, ratio number is available. Yeah. So our question is, based on this percentage number, can we estimate how old is this, how long? Okay? Yeah. Yeah. The point when this mummy was dead, that point, right? Yeah? Because if that mummy, before it was dead, then in that person's body, because recycling, carbon 14 keeps recycling, right? Yeah, recycling. Old is gone, new carbon 14 get in, right? So you can treat as it's a stable, amount, and not in decay. But after that person was dead, there's no recycling, right? Yeah. Then it becomes decay. Yeah. So we calculate from the point that mummy was dead, then start decaying. Okay? Yeah. So then we can use the decay model to estimate the time. Yeah. All right. Yeah. Analysis. But we need to know the half-life of the carbon 14. If the half-life is not known, how do you estimate? But the half-life of carbon 14 can be derived by experiments, right? Yeah. People can, use scientific methods to determine the half-life of carbon 14. Yeah. So we assume that number is available. Yeah. It's known. Yeah. Before we try to solve that problem, that number is available. Yeah. All right. Now, the question, how to use this half-life number, 5,715 years. Yeah. That number we want to, and this percentage number, then we want to find the time, so how long? Yeah. Yeah, between the dead point and the 1991 point. Yeah. Those two time points. Yeah. How many years? Yeah. Between those two time points. Yeah. All right. So then, modeling. Yeah. Solve that problem. Yeah. Yeah. Because we know we can use decay model here. Yeah. The situation the same as our first problem, the radium, right? Yeah, that decay, radioactive. Yeah. But our half-life, capital H half-life, is this number. Right? Yeah. All right. Yeah. And the amount of substance, we use a function y of t. Yeah. Y of t. Okay. All right. Yeah. And initial value, y of 0 equals y0. Yeah. We don't need that specific number. Okay. That number is not important because we will cancel out. Okay. That y0 number will be canceled out. So its specific number is not important here. Yeah. So here we just use the notation, the symbol there. All right. All right. Yeah. Yeah. And here we want to estimate this function value. Yeah. Yeah. Because, it's hard to do a very accurate, just approximate description here. All right. And carbon C12 is common. Yeah. So then, in human body, most part carbon 12. Yeah. Then small amount carbon 14 and rare carbon 13, very rare. Yeah. So very rare we can ignore. Yeah. Yeah. It's a small number. Yeah. So right. All right. Yeah. So then, this number is small. All right. Yeah. All right. So here, so we use that ratio. So we want to, do the estimate. All right. Yeah. Yeah. And because when we use that ratio, carbon 12 at the denominator, we assume amount of carbon 12 never changes in the organic object. Never changes. Carbon 12 never changes. Okay? Relatively stable. Yeah. Yeah. Because in that way, then when we consider the ratio carbon 14 over carbon 12, the ratio, then we can use that half-life concept. Yeah. All right. All right. So now let's write our differential equation. Yeah. Y prime equals ky. Y prime dy over dt. Yeah. So here y prime equals ky for some unknown constant k. Yeah, here the k is unknown. Yeah. We know some negative number, but it's unknown. Right? Yeah. Although it's unknown, because half-life is given, we can find the K value from the half-life. Yeah. So K and half-life, we only need to know one of the two numbers. Then we can get the other one. Yeah. So here, half-life is given. So K can be calculated from the half-life number. All right. Yeah. All right. Yeah. So negative number. All right. Solution. Yeah. We just apply the general solution for the decay model. Yeah. So we can write, by our previous experience, we can write the solution should have this form. Yeah. Y of t equals y0 times e to the kt, based on the decay model. Okay? Yeah. All right. So now we can do the remaining part of the calculation. Yeah. Half-life. This time we need to use the half-life information here. All right. If we plug in time capital H, half-life time, yeah, all right, yeah. So then we get 1/2 of the original amount y0, right? So 1/2, yeah, 1/2 of the original amount y0, 1/2. Okay, all right. So you can see y0 can be canceled out. Yeah. So when we here after the cancellation, we get a 1/2 equals e to the k minus h. 1/2 equals e to the k times h. H is known, so you can find the k if you want, right? But the question, we don't have to find k, right? Yeah. So we can get around. So we can bypass. We can bypass that k. Yeah. Yeah. So, all right. So let's continue. Yeah. All right. Yeah. Because we haven't used this 52.5%, right? We haven't used that number. Okay? Yeah, we haven't used it.
I'm a little confused on how the initial, the y0 cancels out.
Yeah. All right. So you look at here. Yeah. Y of capital H equals 1/2 y0, right?
Oh, so you just, I see now.
Right. Yeah. Just do that cancellation. Yeah. All right. Yeah. Yeah. So after that, now, because next we need to use this information. We haven't used it. Okay? Yeah. Now, T1. Yeah, because this percentage, this 52.5%, we need to find the age, the approximate, the age, that age, we use T1. Okay? T1. At this T1 point, that ratio is 52.5%. Okay? 50. Yeah. This 52.5%, very close to 50, right? 50%. 50 corresponds to half-life. Yeah? So here, actually, this point, time location, time point, very close to the half-life. Yeah? They're slightly different. Yeah. 2.5 difference. Okay? That's small difference. Yeah. But we want to calculate it. Yeah. So you expect the answer should be close to this half-life, this many years. Yeah. But shorter or longer? Can you estimate before this half-life time or after half-life time? Yeah. Shorter, yes. Yeah, because after some more time, you get half-life, right? Because decay from 52.5 to 50 based on the decay, further decay, right? Yeah, further decay, you get 50%. Yeah. Oh, sorry. Yeah. All right. Yeah. So at the T1, we have this equation. Yeah. Now we want to calculate T1. Okay? Yeah. Yeah. All right. So here, we know T1 should be less than capital H. Yeah. Yeah. Less than that. Yeah. All right. Yeah. But let's calculate it. Our last step, we want to calculate. And although if you want, you can calculate K first. Yeah? Yeah. Because we have enough information to find the K. Yeah. But here, we can get around it. Yeah. Yeah. All right. So here, the reason, yeah, these two methods, yeah, I already explained a little bit before, right? Because error accumulated. Yeah. So if you have many intermediate steps, then your errors will be, accumulated, have larger errors. Yeah. All right. So here, we try to eliminate the K. Yeah. Yeah. So we have these two equations. Let's take a logarithm, natural log, both sides. Yeah. By taking natural log of both sides, yeah. Okay. We have these two equations. Yeah. Then division. We take division of these two equations, so K and K cancel out easily. Okay. Division. Right? Yeah. Both sides. We take division. All right. Yeah. After the cancellation, T1 over capital H equals, ratio of these two log numbers. Yeah. Then we write T1 equals this number. Okay? All right. H. Right? Yeah. Then you just apply calculator, right? Yeah. Or you can use Wolfram alpha. So that's what I mean. In this place, so you can use any calculator, okay? Yeah. So the online calculator, Wolfram alpha, yeah. You just, type those numbers in. So you get equals 0.93 H, 93% of H, okay? So the T1, the number of years for that time period, 0.93 times the H value, approximately 5,315 years. Okay? Yeah. Yeah. So that's your estimate. That's your estimate. See? Yeah. Yeah. At least you have a scientific method to estimate, right? It's not a baseless. You just pick some random number. It's not that, right? Yeah. Yeah. All right. So here you can see, yeah, this decay model is so simple, but it can solve this problem, radiocarbon dating problem, and the inventor won the Nobel Prize, so it's an important problem. Yeah. But the method is that simple decay model. Yeah. The first model we learned in this class, you can see, but its importance pretty big. Yeah. Think about that. Yeah. Some simple method could be very useful. Although it looks so simple, yeah, yeah, but its importance could be very big. Yeah. So from this example, you can see that. Yeah. All right. Yeah. All right. So we complete everything of this part A. Yeah. So then I will post some questions based on part A. Okay. Yeah. Some concept questions and some computation questions. Okay. Yeah. Yeah. So I can find some those problems. So then I will post as a self-study exercise questions. Okay? Yeah.
And you're posting the answers to those as well?
Yes. Yes.
Those are separate from the homework, right?
Separate from home. Yeah. Homework we need to build up. We need to learn enough materials. Then we do a, yeah. So, yeah, I will say after we complete 3 weeks material, then we can do the first homework assignment.